Okay, let's get started. So today's class on transmission diagnostics or transmission diagnosis. I kind of designed this class around the idea that most technicians aren't what I would call transmission technicians, in that they don't generally get into tearing them apart. Um, I know when I was starting out, especially when I was with Ford back in the early years, I was a tune-up drivability guy, but I was also a transmission guy. So, 20 years ago, I was tearing transmissions apart. I don't do that much anymore. Where we're at with transmission today, basically, is we diagnose them and then let the shop decide whether they're going to pull it and have somebody rebuild it, or whether they're going to fix it in chassis or something like that. But that's kind of the premise for today's class. Now, as we're going through this, I'll stop at the end of each section, or about every 15 minutes or so, and we'll give you guys a chance to ask any questions. I'm keeping an eye on the chat box, so if you do have any questions, just and as they pop in, just type them in. And when I stop for the discussion, I'll try and answer the questions at that time. So to give you some background, when I got into this thing, transmissions were fairly simple. Pretty much everything was 3-speed. 4-speed were just starting to come out. And a lot of shops at that time rebuilt transmissions. However, over the last little bit, that has changed dramatically. I can remember a time when General Motors had like 4 transmissions. Now they've probably got 15 or 20, and it's the same for Ford and all the rest of them. So it's getting harder and harder to stay on top of what these guys are doing. And to add to it, a lot of them are not rebuildable. And in a lot of cases, the cost of rebuilding one is more than the cost of a replacement. You can get like a dealer drop-in with a good warranty on it for less than you can actually overhaul the darn thing yourself. And in a lot of cases, they come with a better warranty. So there's a lot of sort of pros and cons as to how you're going to go about fixing it. But you do need to do a little bit of research there when you're calling for a box or something like that. So my kind of take on this, in most cases, if the transmission fault is external to the gear train, then it's simply a matter of replacing component on the valve body, or like a lot of them today, the valve body with the solenoids and the transmission control module are a single unit, which is, that's fine. We can do that kind of stuff. But if the problem is internal into the gear train, then the entire unit's going to have to come out to be replaced or rebuilt. So short of rebuilding these things, pretty much every technician out there is capable of replacing valve body components, that kind of stuff, and they're more than capable of doing the re on them. So the type of work that we're going to talk about doing, everybody here is capable of doing it. So the diagnostics is kind of what sets it apart as to whether you're going to be able to fix it sort of in car, or you're going to have to pull it and have it rebuilt or replaced, or whatever the case may be. So we're going to take a look at some strategies to figure out exactly where the problem is. We're going to take a look at a fair bit of scan data as we go through this to assist you in your decision making. We're going to take a look at some service manual stuff too. Not that I'm a big fan of trouble trees or that kind of stuff, excuse me, but there is some good information in some of the code charts and that kind of stuff, especially where it pertains to what the transmission controller is looking at as far as setting the codes. We'll talk about ways to pinpoint some of this stuff, and then the ultimate goal here is for you to make a decision on whether you're going to fix it, replace it, or sublet it out. So the approach is always get the customer complaint in detail. In a lot of cases, that may require you to road test the vehicle with the customer, especially if it's not obvious what the guy's complaining about. Then you kind of got to get your, once you understand what the customer's after, you do have to take some time to kind of understand the problem that you're faced with. And I know that sounds simple to say, but it can be quite a bit different when you get in there. So it's not as simple as it sounds. And I always stress when it comes to transmissions, check the transmission fluid. And I get that, especially on a lot of this late model stuff, that can be difficult checking for the levels. I've got an example in here on a Dodge truck where checking the level was, it's hard. A lot of these things now you got to put them up in the air. You got to buy a dipstick for them or whatever the case may be. And I used to be pretty adamant about smelling the fluid, but I've seen a lot of late model stuff where the fluid looks okay and smells bad. There's really nothing wrong with it. So smell's not as important as it used to be. But regardless of how hard it is to check the transmission fluid, it does need to be checked, especially if you've got range codes or gear ratio codes or that kind of stuff. And then you're going to get into it, scan it for codes, look at some data, try to get an understanding of what the codes or the data are telling you. And then you may want to do a little bit of research, check if there's any TSBs on your particular problem, calibration updates, that kind of stuff. And then perform your diagnostic tests. Now, in some cases, and I'll give you some examples of this as we go through here, you may have to design your own test because you may not have the equipment or the ability to do the test, a particular test, in the way that the manufacturer wants you to do it, because a lot of times, especially with transmissions, at the dealership level, they have a lot of specialty tools designed around, this special testers and stuff that kind of plug into the bulkhead connector, and they can literally drive the transmission with some of these test boxes and stuff, check solenoids and that sort of thing, and we just don't have, we don't have access to that stuff. So there were, you may run into a situation where you have to do a workaround or get creative or whatever the case may be. And then once you've done all that and you've figured out what's wrong with it, you're going to have to make a decision on what you're going to do with it. Some things to keep in mind: engine issues can affect transmission operation, especially when it comes to shift feel, shift timing, shifting late, shifting hard, shifting early. A lot of that can be attributed back to the engine itself. And then the same thing or the reverse is true. A lot of issues with transmissions can affect engine operation. So a lot of times you're going to get a customer that's complaining about the way the engine runs, or it goes into limp mode, or whatever the case may be. And there may not be anything wrong with the engine. The problem may be in the transmission, and that can be somewhat hard to sort out. A couple of things to keep in mind. Typically, transmission issues don't give you fuel trim or oxygen sensor problems or wideband airflow ratio problems. So if you've got a car that's shifting early, shifting late, and your trims and that kind of stuff are okay, it's probably not anything to do with the engine. But if you get in and your trims are all wonky and it's shifting, early or whatever the case may be, then I would go after the fuel trim stuff first, get the engine running right, and then come back and re-examine or look at the transmission after you've got the engine sorted out. Some other things: misfires can inhibit TCC operation. Hopefully, if it's misfiring, it's going to set a code for that. But until you can kind of separate out where your problem is, it's best to treat the transmission and the engine as a single unit. And once you've determined that the problem is with the transmission, then you can stop doing that. But until you get your head wrapped around the problem, best to sort of treat them both as a single unit. Now, when it comes to understanding the problem, this is an example I use in some of my transmission classes. And this is an old one, but it is a good example of a strategy failure. So this is a 1998 Ford F-150 with a V6 in it. The customer's complaint is it bucks and jerks, sometimes set the transmission solenoid codes, and it does set a P1746 on a road test. So this is pretty much what the shop told us. And it was very accurate. The truck was doing exactly what they were saying it was doing. So here's the code, and the code is for a pressure control solenoid A open circuit code. So this is obviously some kind of electrical issue with the circuit. But the question I have is, could this code cause a misfire? Well, When we road tested the vehicle exhibited the symptoms as described by the shop. So, they're dead on in their observations. In order to cure the misfire, they had done some work on it. Spark plugs, plug wires, coil pack. This was a V6 with waste spark. They did an injector flush and a compression test. And the problem here was they were chasing the misfire, and they weren't concerned about the transmission code. They wanted to get the engine running right first before they tackled the transmission, which if they'd treated the whole thing as a single unit, they probably could have avoided some of this. But unfortunately for them, the transmission code wasn't investigated right in the beginning. So when we got the truck, we took it out, we drove it, and we drove it into the misfire. This is the misfire screen from the Ford IDS. I think it's one of the better misfire screen that's out there. And I like the way it continually traces over and over and over itself, so you can kind of look where the tracing is going and see predominantly where the misfires are. But I put a little header in here. Do you notice anything particular about the misfire? And the answer is yeah. Sometimes when this thing misfired, it misfired on 4, 2, and 3, and other times when it misfired on 1, 4, and 5. But it was always the same grouping of cylinders. So that to me is kind of an indicator that this is not an ignition misfire or anything like that. Generally, when you see this type of stuff, it's a strategy and not a failure. Now, what was happening here was Ford, back when this thing was built, they were trying to reduce torque into the transmission so that they didn't burn up the transmission. So in this particular case, they did that by shutting down the fuel injectors, which was the reason for the misfire, but it did severely limit torque. Now, this was an old Ford strategy before we had drive-by-wire stuff. A modern Ford would have went into some kind of limited power mode, and there should have been a code for that as well. The idea being here that you need to separate, is it the transmission causing the engine or the engine causing the transmission? In this case, it's transmission causing the engine to run poorly. Now, the unfortunate part about some of this, when you look at the code, there's nothing in the code description, actions taken, that kind of stuff, to let you know that the car is going to go into some kind of torque management strategy. That has gotten better as we get into newer and newer trouble codes, and generally on modern cars, especially drive-by-wire cars, if the computer is throttling the engine back for whatever reason, there will usually be some kind of code in the engine controller indicating that torque is being managed and to not chase the low power issue, chase the other thing. And then check fluid. I put this in here. This is the 2013 Dodge pickup fluid check. And this was a vehicle we looked at, and it was doing all kinds of goofy things. It was clunking and banging, and it was setting gear ratio codes and that kind of stuff. And we spent a lot of time on this vehicle because when we wanted to follow our routine, which was check the fluid early on. And then when we looked at the routine for checking the fluid, kind of went, well, you know what, we'll just skip that for now. And it turned out to be a big mistake because what was wrong with it was the output shaft, where this was a four-wheel drive, where the output shaft goes into the transfer case. The seal had leaked, and the transmission fluid was being pumped into the transfer case. So this thing was low on fluid, and that's all that was wrong with it. Once, when we finally got around to checking the fluid, which was a pain in the butt, we realized it was low. We filled it up, took care of the transmission problem. Still had to fix the seal on the transfer case and what have you, but it's a good example of where not checking the fluid when we knew we should have been checking the fluid cost us a lot of time and a fair bit of headache. Okay, so it's not easy, but it is necessary, and I can't emphasize this enough. It's one of those steps that shouldn't be skipped over. Next, we're going to kind of take a whack at codes here. Codes come in two varieties: circuit codes. So these codes indicate an electrical failure of a specific circuit, sensor, actuator, or solenoid, and they're generally pretty straightforward. The other side of the coin here are these things called performance codes. Performance codes are pretty open-ended in that they indicate that a command was given but not carried out. For example, the TCM requested that the transmission shift from third to fourth, and it either skipped fourth or didn't ship out a third or something like that, but it commanded a gear change or a torque converter lockup, and it didn't get it. Now, the unfortunate side of this is it really doesn't know what's wrong. It could be electrical, it could be mechanical, it could be hydraulic. Unfortunately, with performance codes, the problem areas get to be much bigger. So circuit codes, as a general rule, are pretty easy to deal with. Performance codes, on the other hand, you have to be pretty careful with them. So when dealing with codes, there may be more than one code stored. For example, if you get a circuit code for a shift solenoid, you may also get a performance code. Well, in that case, a shift solenoid not working right can cause a shift timing or a shift error. So you'd obviously fix the circuit code first. So what we tell guys to do is sort through the codes and only diagnose the codes that pertain to your problem. So there's a little bit of thinking has to go on here, because some faults will set multiple codes. You guys are used to that. You see that with engine stuff all the time. And you're going to kind of have to take a look at the codes that are set, what the vehicle is doing, and decide pretty much which ones you want to pursue. For example, this is an older Volkswagen, and I use this car in a fair bit of case studies, but it's got a vehicle speed sensor code, a gearbox speed sensor code, so a G68 and a G38. I believe that's the input and the output shaft speed sensors. And then it's got an implausible, gear monitoring plausible signal, which means that it's seeing a gear ratio error. Well, do you chase the gear ratio or do you chase the sensors? And the obvious answer is you chase the sensors, because the computer is using the sensors to figure out what gear, whether it's getting the command that it asks for. So if it asks for second gear, it knows what the gear ratio is for second gear, and it would be monitoring the input and output shaft to see whether it's actually getting that or not. So here I would chase the speed sensor codes first and then go back and reevaluate the gear ratio code later. And then we have this type of code, which is basically a circuit code. So in this particular case, we've got a code. If you read the code, they're not going to read it to you, but it's very specific as to which solenoid is defective. There's some information there on how it drives the circuit, all that kind of stuff. But just looking at the wiring diagram, you can see that it's power side switched because the solenoid is constantly grounded. So that would be a fairly easy code to test. But when you get into this stuff, gear ratio codes, it's a different ball game altogether. And I just, the DTC description that I've got shown here is straight out of the service manual. This code is set if the value of the input shaft speed is not equal to the value of the output shaft when multiplied by the second gear ratio when the transmission is engaged in second gear. This malfunction is mainly caused by mechanical troubles such as control valve sticking or solenoid valve malfunctioning rather than an electrical issue. And that's kind of the logic behind the code. But then when you go in and you look at the list of possible causes for this thing, they have basically thrown everything at it but the kitchen sink. You know, it's like everything. Tony asked the fact that the Ford didn't set misfire codes would be a clue as well. Yeah, it can, but we have seen those transmission issues set misfire codes. But yeah, that would be a clue as well. So pretty easy to differentiate a circuit code from a performance code. Circuit code's easy, performance code's not so much. So when dealing with performance codes, if you've got circuit codes, common sense says fix those first. And then if you don't have any circuit codes, then you're going to have to determine if the fault is in the control system or the mechanical/hydraulic system. The control side of things, you're probably going to be able to fix it in car. Mechanical or hydraulic means it's going to have to come out and be rebuilt or replaced. So how do you sort of separate it out? This is done by observing data and monitoring components with a scope or low amps probe while testing the vehicle. And just to let me give you one more thing on this, you can have problems with solenoids and that kind of stuff that don't set codes. They could be leaking hydraulically, that kind of stuff, or they, it's not impossible to have a check ball or a pintle stuck or something like that. So there are. This sounds easy in theory. It's not quite as easy as it sounds, but we'll walk you through some of this stuff. And then this is just sort of following through with our routine check for TSBs. So here's a case of a 2000 Chevy Equinox. It's got a TSB in it for transmission oil leaking from the transmission vents, and they want you to replace the transmission case cover channel plate gasket. Now, if you're not having a problem with oil leaking from the transmission vent, then there would be no need for you to follow this TSB. You may want to suggest to the customer as an update, but if your problem is a missed shift or something like that, and you see this TSB, it's probably not going to, fixing the leak's not going to fix your problem. It's kind of where I'm getting at with this. The other thing with transmissions is, especially with a lot of the new stuff, there's a lot of updates for transmissions. Now, I'm a big fan if there's an update and you've got a problem with the box, you're probably going to want to do it. I wouldn't say that I would do it first. My own preference is spend some time with it, get a handle on the problem. If there are any updates, you're going to do them as part of your repair for sure. If you can't find anything wrong and there's an update, I think you're obligated to do the update, but you kind of get the idea. I mean, if the car comes in, I don't know, for an oil change and you happen to scan it, there's no codes, working fine, the customer doesn't have any complaints, and I don't know, you do a search and you find that there's an update for the program, for the TCM or the transmission, I wouldn't just go ahead and do that, because I mean, the guy's not having any trouble, nothing wrong with the way the car is running. So I think that's just a little bit of an oversell. However, if it is having problems, it's setting the codes that are listed here, or even if it's not setting them and you're in there and you're doing work on the thing and you find that you've got, I don't know, a bad vehicle, an output shaft sensor or something like that, you may want to perform this update just to kind of head off any trouble that this particular issue may cause down the road. And again, that's a bit of a judgment call. Definitely, if you're getting these codes or you can't seem to find anything else wrong with the thing while you're working on it, and there is an update, I think at that point you're obligated to do it. You really don't have much choice. And I keep telling this, I anytime I do a programming class, I kind of send this out there. We have typically relied on TSBs and that kind of stuff as a guideline as to whether or not there is an update for a particular module, transmission, engine, whatever. We get a lot of calls from shops to go out and program, modules, and you ask why. Oh, well, there's a TSB on it or something like that. So TSBs is primarily what technicians use as a kind of an indicator as to whether or not there are TSPs available, or sorry, updates available for controllers. I'll tell you right now, probably only about a third of the updates that are out there for the different vehicles are actually listed in any kind of a documentation or document of any kind. My advice to you is if you're working on the thing and you're not getting anywhere and everything seems to be okay and yet it's still not acting right, then I think you need to go into the manufacturer's website, either with your Joy 2534 box or something like that, and just check and see if there's an update available. Do not rely on TSBs as your primary source as to whether there's a flash available for it or not, because in a lot of cases, the manufacturer will put the flash out there expecting that when the car goes into the dealership for service, they're going to update it. And that doesn't necessarily hold true in the aftermarket, but we still need to check. And then we get into diagnostics. I'm just using this as an example. So I've got a P0750 on a 2009 Dodge Ram, which is a low reverse solenoid circuit. So this is pretty straightforward. This is a circuit code, and the descriptor up top says this DTC is strictly an electrical fault and cannot be caused by an internal transmission failure other than an open in the transmission solenoid transmission range assembly. So they're basically telling you this is a circuit code. Don't worry about the box. This isn't the box problem. This is simply some kind of an electrical failure. When you start to test this thing, down around step 5 there, which I've highlighted with the little red box, it says to install the transmission simulator number 8333. That would be a Chrysler specific test tool, be part of their dealer parts or their dealer tool package. I can't imagine anybody in the aftermarket having one, nor could I imagine anybody in the aftermarket going and buying one, because you would never get a return on the darn thing. So anything in the service manual from here on in, especially in the trouble tree, is pretty much useless to you because you can't do the test the way the manufacturer wants you to do the test. So how do you get around it? Well, you take a look at it. This is the wiring diagram for the transmission in question. If you take a look at it, we can see that it is power side fed. So power is going into the solenoid assembly. Let's see if I can't draw this out for you. Give me a second here and I'll get a pen going. So power comes in over here through the solenoids, and then the computer simply grounds the circuit. So it's a pretty easy circuit to understand. However, we really don't have much in the way of information on resistances and that kind of stuff because the manufacturer has a different way of testing these things. Now, the good news here is there's more than one solenoid in this thing, so we can use some of the other solenoids for a comparison. Okay, so it is a simple circuit, but we do not have the simulator to test it. That's not as bad as it sounds. So we could do resistance tests on it. That's no big deal. I mean, we could go across with an ohm meter and measure all the solenoids. You know, the ones that aren't setting the code to be used as known good. So measuring the solenoids in this particular case revealed no faults. Test the wiring between the PCM and the transmission. Didn't see anything there. And then this is the last step in the trouble tree. And, you know, even though we didn't do it the way they want, we checked resistances, checked wiring, that kind of stuff. Everything kind of comes out okay. And the way this works is if no problems are found, replace the PCM. Well, I don't know about you, but I'm not real happy replacing a PCM at this point. I don't think that's called for quite yet. So can we improvise beyond simple resistance testing of wires and solenoids and that kind of stuff? And the answer is yeah. So, you know, how does the circuit work? Well, solenoid power is provided on pin 10. See that in the diagram right here. PCM grounds the circuit to control the solenoid. Okay. Can we devise a test that will properly test the circuit and tell us where the problem is? Well, I think we can, and we can be a lot more accurate than we can with an ohm meter. So, can we come up with some service specifications we can use for a test? And I think the answer is yes. If you have other solenoids in the valve body we can use for comparison. Since none of the other solenoids are setting codes, they must be normal. The question now becomes, what is the PCM looking for to set the code? And this is probably the most important bit of information in the trouble tree. So when you go back to it, we see some stuff here that's really helpful to us. This is really what I use trouble trees for. Theory of operation, monitoring, and set conditions. Those are really, that's all you really need from a trouble tree. So theory of operation, this is how the circuit is tested. So each inactive solenoid is turned on for a few milliseconds and turn off. Well, if we turn a solenoid on and off, it's going to produce a voltage spike. Each active solenoid is turned off for a few milliseconds then on. This pulsing of the voltage of the solenoid causes an inductive spike, which can be sent by the transmission control module. If an inductive spike is not sent by the transmission control module during the continuity check, it's tested again. If it fails 3 times, that's what sets the code. So we know what the computer is looking for. The other nice bit of information is this when monitored. And it says initially at power up and then every 10 seconds thereafter. So all of these circuits are tested every 10 seconds when the vehicle is powered up, not in drive, because that we couldn't do it while it was driving down the road. But while the vehicle is sitting there in park, we know that the transmission is going to test these solenoids every 10 seconds. I don't even have to have a Chrysler scan tool to make it do this test. All I have to do is flip the key on. So we're looking for a voltage spike, and we're looking for a voltage spike that is different on the solenoid in question. So obviously we're going to have to do this with a scope. So here we are. This is taken on startup, and you can see we've got 3 different solenoids being monitored here. The low reverse solenoid, the voltage spike is much lower than the other 2 solenoids. So that's a clear indicator that there's something wrong here. Now, typically, you're going to have 1 or 2 problems here. The source voltage is the same. You can see that because all solenoids are drawing about the same amount of voltage down through this section. It looks like they're all being grounded, but when they let go, the inductive kick isn't high enough. So what could do that? Well, low power, poor ground, which we don't seem to have, or a short in the solenoid. So all I'm going to do now is we're going to add an amp clamp in here to see if it's shorted. Then we should have more amperage than the other 2 solenoids because the resistance of the shorted solenoid would be low. Therefore, I should have more current flow. So here are 2 inductive kicks off of this thing. On the left, we've got the low reverse, current and voltage. And you can see that this guy's drawing almost a full amp, where the 2 C solenoids only drawing about 3/4 of an amp. So I've got a 1/4 of an amp difference in current flow between the 2 solenoids and a low inductive kick. So the conclusion that I'm drawing here is that the low reverse solenoid is shorted. So even though we didn't have the correct tester, that kind of stuff, we were able to improvise enough to be able to test this thing even without the special tools. So I'm going to take a second here And if anybody has any questions, please take a second, type them in. I got a question. Is this data from a scan tool? And the answer is no. The screen that you're looking at here is from a picoscope. There wouldn't be anything, we couldn't do anything like this with a scan tool other than turn the solenoids on and off. We'd have to monitor them with a scope. I wouldn't even say you could monitor them with a voltmeter, because a voltmeter wouldn't give you the inductive spike, nor would show you the peak current here, because the event is too quick. I mean, we're talking a few milliseconds on time here, so a voltmeter wouldn't catch this. So the only way to catch it would be an inductive amp clamp and a scope, which is what we're using here. Next up is transmission monitoring. Pretty much every transmission in the world kind of does it this way. The torque converter or torque converter lock is basically the difference in speed between the input shaft or turbine speed sensor and the engine RPM. So if the torque converter is not locked up, those two shafts will be spinning at different speeds. And if it is locked up, they'll be spinning at the same speed. And then we've got the gear train being monitored. And basically, we've got all of our different gear ratios, so the computer knows how fast the turbine or input shaft should be spinning, as opposed to the output shaft. And from there, it can determine whether the correct gear ratio has been selected or not. So this is how the computer knows whether the torque converter locked up, whether the torque converter is slipping. It also knows whether, it commanded second gear, whether it got second gear, or it commanded second gear and it got fifth, or whatever the case may be. So monitoring as far as what the gear train is doing and the torque converter is pretty straightforward. To give you an example, generally what we look at is when we're looking at data, and if you take a look at it, my green trace here is the current gear. So this would be 4, 3, 2, and first. So this would be a 4-speed. And if you take a look at it, every time a gear change was commanded, we look at engine RPM. So if I command a gear change, should the RPM drop? So I command a gear change, it drops. I command a gear change, RPM drops. I command a gear change, RPM drops. I command a gear change, RPM drops. And then I've got my transmission input shaft speed sensor in red. So the difference between the red line and the orange trace would be torque converter slip. So here in the lower gears, the torque converter is slipping all the time. And then as we're partway through third gear here, you can see the computer bring the torque converter on. And now the torque converter and the engine RPM are actually traveling at the same speed. And then right here on the 3/4 shift, you see they come apart for a second. And all that means is the transmission control module uncoupled the torque converter to make the shift, and then it brought it back on again. So in every case where we commanded a gear change, we got a gear change, and we can actually tell from this whether the torque converter is locking up or not. Okay. So it's pretty easy to monitor this stuff. I like to do it graphically if I can. But you kind of have to know what you're looking at here, and it is pretty straightforward. Now with some of the newer transmissions, the screens get pretty busy, just from the fact that you've got a lot more shifts taking place. But having said all that, I don't really even bother looking at this data unless there's like codes or concerns that I determine are in the transmission. So if I had a car that was down on power and the customer complaint was it was shifting early and light, and I went in and I looked at fuel trim data on the engine and it was off, then I would spend my time figuring out the fuel trim problem as opposed to this. Most of the transmissions that we deal with today, if there's any issues with um, gears not being commanded or that kind of stuff, the monitoring on them is so tight that it's almost impossible for a fault to slip by the computer, especially on the newer stuff. And I'm going to talk a little bit more about that because there's some other issues here as well. But just looking at the speed sensors and stuff alone here, we can monitor these things and what they're doing pretty easily. So when it comes to diagnostics, the question you kind of got to ask yourself, if a gear shift is commanded but does not take place, or the torque converter is commanded on and does not lock up, then did the computer do the right thing? Did it turn the solenoid on? Did the solenoid operate properly? So that means the solenoid must be tested for mechanical movement and electrical integrity. I like to do this with a low amps probe if I can. Now, how you do this to a certain extent is going to be dependent upon what the manufacturer allows you to do with a scan tool. Some of the other things that affect this are location of the TCM, if it's internal to the transmission, are there external wires controlling the solenoids, that kind of stuff. All of this is going to determine what you can and can't get away with on any particular car. And unfortunately, a lot of the valve bodies now are incorporating the TCMs into them. So the valve body is, it still has spool valves, but it now has all the solenoids, and the TCM are all internal to the transmission. So getting at the wires that run to the solenoids is a little bit more difficult than going through a bulkhead connector now. Having said that, these solenoids are still powered through the bulkhead, and pretty much any transmission that I've ever worked on that had the transmission controller inside the box, you had pretty good bidirectional control with the scan tool, which means you can literally in the service bay get around the power wire that feeds the valve body and command the solenoids on and off and watch what they're doing on a scope. However, you're going to have to modify your test to match the situation. So that this, how the car is built, where the stuff is, and all that kind of stuff is going to dictate how you go about doing your testing on this stuff. So when it comes to diagnostics, and this is just an example, we've got a 2008 Ford Escape. Customer's description here is: inspect where the transmission takes too long to shift out of second gear, and then it seems to skip back to first. Okay, that's a pretty vague description. So we road tested the vehicle, and we didn't observe the skip back to first, so not quite sure what he was talking about there. But the transmission did seem to stay in second gear for an extended period of time. Okay. So we go in and we look at some data here. Right, so we've got RPM, we've got our commanded gear, shift solenoid 1, shift solenoid 2, we got that service information. And from the data that we're looking at here, where are we here? So this would be second gear, this would be second gear, this would be third gear. When we commanded second, it kind of flattened out, and RPM went up because we were accelerating. But right here, when we commanded third gear, there was no change in RPM. It didn't flatten out or anything. It just kept on building. And then when we switched into fourth gear, the RPM dropped. So clearly this thing commanded commanded third gear and didn't get it. Now, we don't know why it didn't get it, so we have to go into this a little bit further. And that's kind of where we're going with this thing. So when we go in and scan it for codes, there's no code, which is very odd on a newer car like this. I suspect maybe the codes were cleared because of the P1000. Not exactly sure. But we did do a fluid level check on it. It was okay. It looked okay, smelled okay. And We went in and did a quick search for bulletins. So there is a bulletin for a harsh 1-2 and a 2-3 shift flare. Well, we've kind of got a 2-3 no shift, so this may apply to our situation. So it's not exactly our concern, but it's worth a look. And we just went ahead and did it anyway because we had our scan tool on it. It made no difference to the way this thing operates. So what we then went in and looked at was what had to happen with the shift solenoids for the 2-3 shift to occur. And if you take a look, SSB and SSC have to change states. So if you take a look at the two gear positions here, in second gear, SSA is on. For third gear, SSA is on. If you look at SSD and E, their position does not change on a 2-3 shift. But if you come back over here to SSB and C, both of these guys change states from second to third. Okay, so that's what the computer is doing to command third gear. So we're using the Auto Ingenuity scan tool here. Our commanded gear is second. Fortunately, the labeling's a little bit different here. So SS1 is SSA, SS2 is B, C, D. You get the idea. So for second gear, I should have on, off, and I have on, off. Now, when I make the switch into third gear, I should have on, off, off. So there I am in the third, on, off, off. So what this tells me is the computer made the right decision. It commanded third gear. So it wants this thing to shift into third gear. And based on what I'm seeing on the scan tool, it's doing the right thing electrically. Now, that doesn't mean the command is being carried out. We still have to verify that, but at least we know the computer doesn't have any logic issues or any of that kind of stuff. It's making the right decision. Now what we need to determine is, are those commands physically being carried out? So we take a look at the transmission and the wiring on this particular vehicle. The transmission control module is built into the PCM. And what we have here is transmission power. Now, they don't show you this, but this would be the power wire, solenoid power down here. This is the power wire that feeds all the solenoids. So these would be the control circuits. Our solenoids are listed. So we're basically going to go through and take one of the solenoids that we know to be working okay, use the scan tool bidirectional command to turn the solenoid on and off. And what we're doing here is we're attempting to get a look at what a good solenoid looks like. So you can see that the three solenoids that are working properly are drawn about 3/4 of an amp each. And I've stacked them up below so you can get a good look at them. So everything kind of looks okay here. And we're going to check for the pintle bump. So the pintle bump in this case indicates a mechanical movement. Now, this is a shift solenoid on a Ford. This is an entirely different vehicle. So pintle bumps, not all pintle bumps look like this. And if you've done a lot of amp testing and that kind of stuff, pintle bumps come in all shapes and sizes. But we've kind of got known good back here, right? And then we just do that as a comparison. So to sum it up, our 2-3 shift is missing. Fluid's okay. The TCM is commanding the shift. The solenoids responsible for the shift are working electrically and mechanically. We saw the pintle bump there. Therefore, there's nothing electronic or electrical or hydraulically in the solenoid stopping this thing from doing its job. Therefore, the transmission, or the problem is in the transmission gear train or hydraulic system, neither of which are serviceable at the shop level. So it's either rebuild it or replace it. Next up is a Jeep Grand Cherokee. Customers complained as the transmission shifts erratically, goes into limp mode, and we've got a check engine light on with codes, and we've got an underdrive pressure switch rationality code showing. Okay, so that's kind of taking us into the transmission. Now this code's a little bit different. When is it monitored continually with the ignition on and the engine running? And the set condition, the DTC is set if the LID pressure switch is in the wrong state for the current gear. For example, this code would set if the underdrive pressure switch remained off while the transmission was in second gear. So we've talked about how they monitor the gearbox and the gear train. A lot of manufacturers also monitor shift timing and clutch fill and that kind of stuff. And how it works is basically the computer knows when it turned a solenoid on. That should result in spool valve movement, which should direct hydraulic pressure to a clutch or a band, mostly clutch these days. And in that circuit, in that hydraulic circuit, would also be a pressure switch. So from the time the solenoid is turned on until the time that the clutch fills, the circuit is pressurized, and the switch closes, the computer is actually monitoring that. And what they're looking for is, did it close within a specific window? And if the answer is no, then they know they've got some kind of a hydraulic issue or something of that nature. Now, it could be the switch, it could be the solenoid, it could be a bunch of different things, but that's how they're monitoring some of these hydraulic channels and that kind of stuff. So a pressure switch really, in this case, is reporting on hydraulic operation. Now, how does the switch work? This is a little bit different. Okay, so the TCM reads the voltage on the switch circuit. The switch is grounded when the switch closes. Now, this is a little bit hard to understand. Okay, so what I've got here, let's get a pen, is this is voltage coming in. Oops. Comes in, goes through this resistor, and up into the PCM. So when the switch is open, I read 12 volts. The reason for that is there would be a big resistor in here as well. Okay. Now, when the switch closes, that takes the circuit to ground, and the voltage drops. So 12 volts on the circuit, switch open, 0 volts on it, switch closed. That's kind of how it works. Okay. And this you could figure out pretty much from a wiring diagram. Once you've got that information, then it's pretty easy to test the circuits. So all we need to know is which position those circuits should be in for any given gear, and we can go through and kind of figure out whether they're working properly or not. So this chart shows which position is which it should be in for any given selected gear. So I'm going to use reverse, and the reason I'm using reverse is all the switches are open. So when I go in and select reverse, everything reads open except for the underdrive switch. Now this could be because of a hydraulic leak or something of that nature, or it could be a problem with the switch itself. Now the easiest way to get rid of a hydraulic leakage type problem is just shut the darn thing off. That shuts down the pump, takes the pressure away, turn the key back on. And that's exactly what we did here. When we turned the key back on with the transmission or the engine not running, the switch still said closed. So now it becomes a question is, well, is it in the wiring or is it in the switch itself? Okay. So how are we going to test it? Well, what we did was basically we took a jumper wire and ran the jumper wire from here to each one of these wires individually. And when we touch each one with 12 volts, we should get, try and get rid of my, we should get the open circuit because they've got 12 volts on them now. This switch or this screen was doctored a little bit by me so that everything read open. They actually were switching back and forth as I was applying voltage or not. But that tells me that the wiring is okay back to the transmission or to the transmission control module, and that the transmission control module understands the circuit. Therefore, that leaves the solenoid body as being the problem with this thing. And I think, if I remember correctly, the solenoid pack was part of the transmission or was inside the transmission. But anyway, you kind of get the idea of how we went about that. Unplugging the switch causes all switches to read open with 12 volts applied. This tells us that the harness and the TCM are functioning properly and that the problem is in the transmission, in this case, the switch assembly, which will have to be replaced. So pretty straightforward. You're on. Next up is a 2004 Acura. Customer's complaint here. Check engine light on. It's got a code 700 and P0113 and a PCM and a 9060 or sorry P0962 present in the TCM. So the 700 means, basically there's a problem in the transmission. So we go over to the transmission and it says we have a problem in the AT clutch pressure control solenoid valve A circuit. And then there's some notes here before you troubleshoot or record all freeze frames. Pretty straightforward stuff. And then clear the codes, retest. Is the code indicated? Yes, you go to step 8. And here they're going to run you through a bunch of resistance tests, that kind of stuff. And it's basically, does it meet the specifications? So you can see here they want me to measure at the solenoid connector, pins 1 and 2, is the resistance within the 3 to 10 ohm spec? Yeah, it's right on. Go to step 11, check for continuity between the solenoid connector and ground. Is there continuity? Yes. So in this case, go to step 12. Step 12 says turn the ignition on, measure the voltage between AT clutch pressure solenoid connectors 1 and 2. Is there about 11 volts as the ignition switch is turned to the on position? Yes, we measured 12.3, so it says go to step 20. Step 20 says update the PCM or substitute. No, good. So if you follow through on everything that's in there, you're going to wind up replacing the PCM on this particular vehicle. So I don't know about you, but how do you feel about putting a PCM in this vehicle? Not too good, at least not yet. Could there be a better way to test the control valve? Well, I think there is. So we're going to take a look at the wiring. We can see that the PCM powers the solenoids. They're permanently grounded. So these are power side switch solenoids. So we kind of got an idea how the circuit works. What will be the best way to test it? Well, let's take a look and see if we can get some information on it. We've got some other solenoids here we can use as a comparison. And then it just becomes a question of, can we manually make the circuit work? And there's the best way to make the circuit work is with a scan tool, obviously. But you know what? If that doesn't work, you can always road test the car. Okay. Luckily for us, this scan tool and this car offered us a lot of options when it came to testing these solenoids with the scan tool. So we basically went in and used the onboard tests to do it. Now, we didn't know what to expect, and we kind of needed to know what good looked like. So there was a few shift solenoids on this thing. So we took a look at some of the ones that were working fine. So this is a scan tool message after running the onboard test on our solenoid A. And again, it kind of looks like the PCM is the problem here. It's just going by that, but we're going to go ahead and test the solenoids anyway. Okay. So we use B and C, and this gives us a baseline for the solenoid. The first thing I notice is the computer, when it runs this test, doesn't just turn them on. it actually pulse width modulates them. But when we look at it, we can see both solenoids are being pulse width at about 13.2 volts, and they're both drawing about 0.6 amps. So both of these guys are doing the same thing. I would expect shift solenoid A would do the same thing. So those are my numbers. When I go over to solenoid A, however, the voltage is down a little bit at 11.5, but the amperage is way up at 1 amp. Well, the reason the voltage is down is because the amperage is up and it's affecting the circuit a little bit. But the bottom line here is the amperage is higher. Therefore, this solenoid's drawing too much amperage. So the circuit is different. Now, is this a PCM problem? And the answer is no, it's not. If it were a PCM problem, we wouldn't have more amperage. We would have less. So this, how do you get more amperage? Well, you get more amperage because of a shorted solenoid, and that's exactly what's wrong with this thing. So at the end of the day, our test actually worked out a little bit better than the factory test, even though the scan tool was passing it, and the solenoid was actually on the outside of the transmission, if I remember correctly. So we were able to bolt a new one in, and away this thing went. Chevy Cobalt vehicle hunts in and out of TCC lockup once it's warm and under light load. Well, that kind of makes sense because when it's in during the warm-up period, it's probably not even trying to engage the torque converter. It's been reflashed at the dealer, didn't help. The customer's original complaint was a surge at highway speed, and we've got no codes. So this was taken while the car was surging. We're looking at our trims. They're normal. That tells me that I'm not really looking at an engine problem. So the engine data does not support an engine problem. Same thing with a misfire counter. We didn't see any misfire. It didn't feel like a misfire anyway. So we went through that fairly quickly. Okay. And pretty much ruled out that the engine is not the problem. Then we started to plot TCC data during the surge, and we can see that there's a fairly large amount of TCC slip. It's actually slipping up over 100. Now, how this works is the thin dotted line is the TCC slip speed. The thick solid line is TCC duty cycle, and the thin white line is TCC release pressure. So there's no pressure to release the solenoid. The duty cycle on this thing is all over the place, and so is the TCC slip. So this is an indicator that the computer is trying to get this torque converter to lock up, but it's not locking up properly. Okay, so it does appear to be slipping, and the PCM is chasing it. We go in and do a quick check for TSBs. There are no TSBs. We do some more digging around, trying to get our ducks all lined up here. And I came across this on an IETN search, and it says the TCC pressure control valve in the body was sticking, scored valve and bore. Great English. Due to the cost to repair, we replaced the trans with an assembly. Thanks for your help. Well, I'm not prepared to do that just yet, but it does allude to the fact that there is some issues with the valve body and the TCC pressure control valve. Now, having said that, we've seen this on other GMs, mostly the trucks, but occasionally on the cars too. So we did find something, not sure if that's our problem yet, and it doesn't necessarily mean that our vehicle has this problem, but we need to be aware of it. Now, General Motors provides these diagrams, these hydraulic diagrams, so that you can try and trace where the problems are. Just as a quick sort of an aside, I put this in here kind of tongue-in-cheek because Nobody that I know of really uses these diagrams when it comes to diagnosing transmissions, but what is required to lock the TC up and hold it? Well, I need good pump pressure. I need the torque converter clutch material to be in good shape. I need the pressure control solenoids and that kind of stuff to do their job. Okay. Now, what can I practically test? Well, I could maybe put a pressure gauge on it. The TCC, how can I tell how much pressure I've got going to the torque converter? Not really. However, if I had an issue with pump pressure or something like that, I would expect to have more problems than just a TCC that's not engaging. Our experience on torque converters, especially on most late model stuff, is the clutch materials and stuff don't fail like they used to. The torque converters are usually pretty hardy, so it wouldn't be high on my list of things to go looking for, which leaves the two solenoids and the hydraulics on the thing. So really what I need to know here is the computer doing its job? Are the solenoids being commanded? That kind of stuff. So the TCM operates the solenoid with a negative duty cycle at a fixed frequency. Solenoid's ability to ramp the TCC, apply and release pressure results in smoother TCC operation. So basically what's happening here is we're going to duty cycle the TCC solenoid to bring the torque converter on smoothly. And it makes some reference here to the fact that duty cycle, when vehicle operating conditions are appropriate to apply to TCC, the TC immediately increases the duty cycle to approximately 42%. So 42% duty cycle starts to apply it, and then it ramps up the duty cycle to approximately 90% to achieve full TCC pressure. I don't like the way that's written. Typically, in my experience, you rarely will see a car go anywhere near 90%, especially at GM, to lock up the torque converter for the simple reason that if you're at 90%, you got no wiggle room. So 90% is pretty high, but at least we know where the torque converter is coming in, or supposed to come in at around 42%. So we know solenoid resistance, duty cycle, increases to apply. It's pulse width modulated. It should start to apply at about 45%, and it should be fully locked up by 90. So what do we need to know from our road test? Well, when the surge occurs and the TCC starts to slip, does it have the right resistance? Is the TCC duty cycle above 45%? Does the slip speed drop to 0? And is the TCC duty cycle actually increasing? So from the diagram, we can deduce that the TCC is ground side switched through pins E and T. Just a quick look at the wiring diagram. A quick ohms check at a solenoid shows that we're pretty much bang on. All right, so that's normal. And then we go out and we start to road test the car. Now, this is a little bit, what am I looking for here? I could have done a better job on getting this out, but basically the TCC doesn't really show it here, but it's hitting 100% on the duty cycle. And even when it hits 100%, it's not slowing down the torque converter. So you can see the slip speed there at the bottom. Right here, we've gone to 100% duty cycle, and it slowed the torque converter down some, but it didn't drag it to 0. And then it kind of flares up, and we can see the torque converter, or the PCM, constantly adjusting the duty cycle to get this thing to lock up, and it just can't get it done. Now, in my experience, TCC slip speed, most of them code at around 75 to 100 RPM slip. in my experience, a good torque converter will not slip 20 RPM. In fact, most of them, when they're locked up at cruise going down the highway, the slip speed is usually somewhere between 0 and maybe 10 RPM. So they can lock them up pretty tight. This guy is definitely slipping. Okay. When we go in and look at the computer, it appears to be doing its job. We know that it's changing the duty cycle, holding the ground on longer. So the computer, it says it's up in the duty cycle. That's certainly what's happening. Okay. So to kind of wrap this one up, the TC is being commanded properly. The PCM is driving the circuit properly. The solenoid has the correct resistance. The TCC is slowing, which indicates some hydraulic activity. We came to the conclusion that the problem is in the valve body or the hydraulic system. And our recommendation was that the transmission valve body be replaced. It was, and the vehicle returned to normal operation. And that brings us to the end of our transmission diagnostics for non-transmission techs.
And please don't forget to follow us on social media, our Facebook page, our YouTube channel. And please make sure you either click the like, subscribe, or follow buttons. Until next time, have a good one, guys.
I'll give you a second or two to do that, and then we'll move on to the next bit.